All right. Good morning, everyone. We're beginning our next session. So I'll start with introducing myself. My name is Wojciech Wiechowski. I'm Project Development Director. I work for RWE Renewables. I've been with the company for almost 12 years. I started working at RWE in the UK with various aspects of bottom fixed projects, and I relocated to the US in 2021. I'm currently looking at various aspects of floating offshore wind. So for those who maybe are not that familiar with RWE, I'm going to say a few words about my company. So RWE is it's a large energy and renewable energy company with headquarters in Germany. We're one of the largest offshore wind developers globally, and we are also one of the first ones. So we developed our first offshore wind project more than 20 years ago. It's, I think, 60 megawatts. So we are also present in the US. US is one of our core markets as well. And besides our quite sizable onshore renewable activities, we have our offshore wind presence. We secured a lease in the New York Bight. It's called Community Offshore Wind. It's a joint venture with National Grid Ventures. We have a floating offshore wind lease in offshore wind California, and most recently we secured a lease in the Gulf of Mexico. So we are a believer in floating offshore wind technology. We have 2 demonstrator projects in operation now in Europe, and we are looking at working on developing our floating offshore wind portfolio globally. So I'm very pleased to be here today to moderate this session, the title of which is Floating Offshore Wind Deep Dive, Engineering Mooring Solutions for US Markets. I'm pleased to welcome our today's presenters. I'm delighted to introduce Bruce Martin, who is Senior R&D Engineer at Principal Power, and who will present the presentation titled Innovative Deep Water Mooring Systems for Floating Wind Farms, and the project name is Deep Farm. Then Bradley Lynn, Senior R&D Engineer also at Principal Power, who will present the topic of his presentation is Demonstration of Shallow Water Mooring Components for Floating Offshore Wind Turbines, and the project name is Shallow Float. And Olivia Burke, Program Innovation and R&D Manager at the Carbon Trust, who will present the summary of National Offshore Wind R&D Consortium floating wind mooring projects. Before I hand over to our first presenter, I would like to make a few housekeeping remarks. So each presenter will take approximately 10 minutes to present their presentations. After that, we'll have 20 minutes for a Q&A session, and following which we will have 15 minutes for questions from the audience. I just want to remind everybody, please use the Slido app, submit your questions through the Slido app, because there will be no live questions taken from the audience. And we aim to finish this session at 12 o'clock. So with that, I would like to invite Bruce Martin. The floor is yours.
Morning, everybody. Those here and those listening in. So, title of this project, as I said, is we're looking at deep water mooring systems for floating wind. This project is basically in its conclusion phase right now, so going to go over most of the key things that have happened in the last year. Just from a project background standpoint, most of the floats deployed to date have been typically in shallow, got about less than 200 meters of water depth, where our typical drag and bearment anchors are remaining a feasible solution. What we're looking to see is in greater water depths, the typical mooring systems, you're going to have much higher vertical loads, and as we heard earlier, These classical anchors are not going to be able to sustain those vertical loads, so we're now looking at needing for piles, whether it's suction or driven, or some other vertically loaded anchors. Generally speaking, the anchors of that type are going to be more expensive to procure, manufacture, and install than dragging bearman anchors. So what we're looking at seeing is for the mooring and farm layouts where it's possible to do this, our shed anchors are cost effective by reducing the anchor count. So what we have here is a typical farm layout if we're looking at everything having individual anchors. Now, if we take it to where we're looking at shed, this is one incarnation of the shed anchor, your classic honeycomb approach. You're dropping your anchor count significantly. So the project's been a little over 3 years looking into this. We've had a wide range of both academic and industry partners. Overall, the overall project team has fluctuated a bit, but it's typically been around 20, 21 people directly supporting 2 students. We've had Principal Power in charge of the overall project. We've had Anchor Solutions working on our anchor design on the commercial track. We use Sand Sea Systems coming into row properties and looking at the potential for inline tensioners. We have working with NREL doing a lot of open source modeling and improving the design toolkits for the open source community. The team at UMass Amherst working on the single asset mooring design and the open source track for the farm level. LCU, and then NREL coming back in and doing LCOE modeling based on the potential cost savings identified over the work. At the same time, we've also been running a parallel track with ABS looking at approval in principle for the shade mooring system at the sites in question. So just once again, a little bit more detail of how the various tasks broke down. We went through a site selection activity. We decided to focus on a California West Coast site that was close to the Humboldt Bay, the current Humboldt Bay site that's being looked at overall. Went through some more components development. Went through a lot of software development on the open source track, improving the capabilities of OpenFast and FastFarm. And then the single asset mooring design, the farm layout and some cable work, and then the overall LCOE reduction. So today we're going to focus more on the last 3 aspects of this project. That's great. So task 4 overall, so we had the 2 paths that we took where we were developing a mooring system for the wind float on the commercial track, and then for the Volta and Semi on the open source track. The primary outcome of this work was to come up with the representative single asset mooring systems we would then use to generate the farms from, and making sure that both systems meet the design requirements so we know we have a viable mooring system to start with for each. So now when we have the single mooring system, the single floater system, now we're looking at building small arrays to create some example scenarios using that classic honeycomb design to look into. So we have six floaters. Gives us 11 anchors. A number of them are single anchor. Then we have shared anchors, both 2 and 3 line scenarios. We then ran through the key load cases for intact strength, operating, and storm to determine the design criteria for these anchors. And then we used those anchor design loads, pass them off to the anchor designer to look at potential for different shared and single anchor designs, or would you do one common anchor design for the entire farm and take advantage of some economies of scale there? What you've got here overall, we're looking at the anchor vertical load comparisons. To the left of the dotted line are all the single anchors. To the right are all the shared anchors. Generally, you're seeing about a 40% increase in vertical design load. Generally speaking, the horizontal design load is pretty consistent across all of them, just for this scenario, because as you can imagine, if the environments are coming from top of the screen, one anchor supports one platform. For the other ones, 2 anchors supporting 2 platforms. The aggregate sum is very similar. So one of the big things that we were looking at is looking at the impact on potential failures of the mooring system. So normally what you're dealing with is we assume a line failure anywhere in the system. So could happen at the failure, could happen all the way down to the anchor. Yeah. So in deep water with these shared systems, what you're going to see is if a single failed anchor or a single failed line, you'll get this large increase in platform offset from the deep water, which is now radically changing your anchor load geometry in that case. So what happens in that standpoint? How do these loads all propagate out? So same case, all the anchors considered, all the single ones unaffected by this. But you're seeing here that you've got this large increase in your horizontal design load for the anchors, just because your two most loaded lines here are now a much tighter angle between them. The loads add up a lot more. So depending on your anchor design, depending on your soil conditions, your damage case, your accidental load case may or may not be your dimensioning scenario. Depends on your site-specific conditions. So previous work that's been discussed here at this forum before has been around, because of the shared anchor conditions, you're looking at needing to increase your overall safety factors to maintain some equivalent reliabilities. So you can either increase those factors of safety such that your shared anchor is not the weak link. Excuse me. Or you can look into how an anchor failure will ripple throughout the system. So what we're looking at here is the failure of a three-line anchor system, where basically you have a geotechnical failure of the pile, i.e. the pile is pulled out, all the lines are still together, hooked up to it, so you now have this large submerged body swinging around, transferring loads everywhere. So what we're seeing is now looking at that. So in this case, we consider this pile to have failed here. All the loads will radiate outwards into these lines, and as you'd expect, you'd see the increases in loads for the anchors, but not to the extent of what would have happened if the anchor line broke. So your anchor line broken is still your most critical case. So on the open source track, we looked into a number of alternative configurations where we're looking at your 3 lines. We're also looking at scenarios for a 6-line shared anchor, where you're still each floater is still 3 lines, but 6 lines are coming together and sharing the one anchor. 6-line anchors are going to further decrease your anchor count, less and less anchors needed. But you're typically, depending on how you set up your array spacing, you're likely to end up increasing your required farm size for the same amount of floaters, or you're gonna potentially have more opportunity for wake interactions between turbines. That's going to be a site-specific layout assessment you'd have to do. And as you'd expect to see, so right here we have anchor load results for a single line anchor, a 3-line shared, and a 6-line shared. And overall, your anchor loads are staying fairly similar, but as you'd expect, the 6-line system sees a lot more sustained vertical loading, because your vertical loads are obviously always present, your horizontal loads are canceling at different points in time. So these high vertical loads could be challenging for your anchor design, and you're going to have to look a lot more at, do you use the same anchor design for all of them, or do you create different classes of them for your project? So we looked a little bit more on how that farm layout affects your AP. So we're looking at the single anchor for all, the 3-line share and the 6-line shared anchor scenario. We're looking at your wake losses effects. So we're looking here for a given wind speed, set of wind directions. What you're seeing is that by going to the various shared anchor systems and sharing your farm layout, you do start smearing out your your weight losses. So depending on the directionality of your environment at site, that may or may not be an adverse effect. Something that will have to be considered on a site-by-site basis. As well, if you want to manipulate and then trade off the floater spacings within the farm as well, those would change too. So it creates a design space that a designer can operate within. So we looked at the true impact of these based on their impact to project overall costs and the LCOE. So NRL came in and used their suite of tools, their cost modeling, their installation scenario modeling tools to basically play the installation scenario out for this site. What we're seeing is that based on shorter installation times for the system, lower costs on mooring, both capex and the installation, and then the component cost decreasing as well. We're seeing overall for a gigawatt scale farm, the use of shared anchors results in about a 2.5% overall capex reduction relative to a single anchor system. So coming out of this, as the project's wrapping up, we've identified a number of areas we want to look at further, either us or encourage others to do so. So we're looking into further identification, optimizing a number of these key mooring design parameters for a shared anchor system, see how they're differing from a single. Would you design your mooring system for the individual floaters differently to make the shared anchors work better or not, for example? Looking into trading off of the various array spacing and layouts on how those would affect your mooring design and costs versus better weight losses. One concern is the impact of having this multi-directional cyclic loading on the anchor's overall holding capacity. There's already an existing NSF study looking into aspects of this. We would look into further cost assessment activities, looking at various alternative installation and project execution scenarios to see the sensitivity of these cost savings based on this. We want to look a little bit further into some more reliability-based assessments of that farm level system to set what the safety factors are. So now that we know how the consequences of failures of the different parts of the system, does that mean that if we are going shared, do we need to consider alternative safety factors for design than what we would typically use if everything was independent? Then you get into the whole wake effects on shared anchor loads. So if you have one turbine operating downstream of another, we all know that wake effects change dynamics. How will those interact? And then for this study, we looked at the classical pile technologies, suction or driven, but this work could easily be expanded to alternative technologies that may be more applicable to the multi-directional environment. So that's all I have for today. I'd like to acknowledge all the great work that the entire project team has brought to bear on this over the last couple of years, and looking forward to taking your questions at the end of the session. Thank you.
Hello, I'm Bradley Ling. I'm an R&D engineer at Principal Power, and today I'm going to be talking about our shallow float R&D project. So before getting into the project, I'll just give a quick overview of the project team. So Principal Power, we're the prime, and we're also doing mooring design and all the project management for the project. We've been working very closely with TFI Marine. They're developing this polymer spring load reduction device for a mooring system. And so the project's really been focused on evaluating that component and helping progress their development of that component for mooring designs. NRL's been also a close partner. They've been doing some open source software development, mooring designs, and then they'll also be doing some cost analysis later in the project. We've been working with Aker Solutions, primarily using their testing facility. We're also working with ABS, pursuing an AIP similar to the last presentation from Bruce. And then the funding agency, of course, is NOWRDC. And so a project overview, we're exploring innovative mooring solutions for shallow water sites, so looking in that 40 to 60 meter water depth. These shallow water sites, as for those of you that were in the last presentation, are challenging on traditional mooring system designs. You see really high peak tension loads. And so the goal here is to see if these load reduction devices, particularly in this project, the one from TFI, can help reduce those peak loads, but also help reduce a lot of the fatigue damage that comes from this, particularly as we go into shallow water and larger turbines. More and more of these mooring designs are driven by fatigue in addition to those ultimate limit loads. You're getting thrust variations from the turbine that's causing cyclical loading on the mooring lines in addition to wave frequency response. And so can we use these load reduction devices to both reduce that fatigue damage, but also reduce those ultimate loads? And ultimately the goal here is to reduce the amount of chain and the size of chain that's needed for the mooring system. I will note also, while this project is specifically looking at these really shallow 40 to 60 meter water depths, load reduction devices don't have to be used only in 40 to 60 meter waters. The same findings here could apply to medium water depth sites as well. So if we look in kind of the water depths where, some of our existing deployments are, this may be a solution, in that 50 to 150 or 200 meter water depth as well. So a summary of just the design basis, so the conditions we're considering for the project, focused on the New York Bight area. We targeted a site in the shallower side, so 50 meters of water depth. It's a flat sandy seabed where, drag embedment anchors are a feasible solution for anchoring technology. And it's relatively mild mid-ocean compared to some other projects we see, relatively low average HS, relatively low 50-year storm conditions compared to some other parts of the world. And then the project, we're considering the IEA 15 megawatt wind turbine for the turbine for the project. An overview of the C-spring technology. So it's a polymer component. So the polymer has been developed by DuPont. It has other industrial uses. It's used often for like very high fatigue sites as a damper. What TFI has done is they've taken that polymer and they have created these shapes that as they deform, create a load response curve that's more favorable for mooring systems. And so what we have here on the upper right is a load displacement plot of a C-spring design. And so what you see is as it first compresses, it's stiffer, and then it actually softens into longer elongation values until these ridges here start to compress, and then you get much more material touching each other, and then it rapidly stiffens. And then actually to prevent overloading of the system, the metalwork actually will engage, and so it will prevent further compression of the polymer, so protecting the polymer material from experiencing too high of loads. So the way that this works, unfortunately, this is a PDF, so we don't have an animation here, but the way this works is actually the two pad eyes that would be connected to the mooring system, as they move apart, as they move in tension, the polymer actually compresses. So there's two separate pieces of metal here that are pulling that polymer together as the entire system extends. So while obviously mooring systems are working in tension, the polymer component part of this is actually working in compression. And so TFI, the developers of this load reduction device, they have a long development history. They've done prior scaled tests with different projects. They've been pursuing DNV certification separate of the shallow float project. And then so what we can, as mooring designers, Principal Power, as mooring designers, what we can do with TFI is we can change a couple different variables of this to tune the response for our specific site. So the main design variables that we have is how much total spring length in a mooring system do we have, so how much energy can you absorb through that, but also the spring load rating can change. And so, particularly if you're looking at a farm level deployment, TFI can take this same shape and scale it up or down in diameter and wall thickness to get to different load ratings. And so when you change that, essentially this curve just scales vertically for different size springs. And so as part of the project, we had two different design tracks. We had a proprietary design track, but then also working with NREL, they did an open source design. And so that first started with some updates to the OpenFast modeling software. So they added the ability to model nonlinear mooring components to OpenFast. And then with that, they then took and did an open source design at the same site, the 50-meter water depth in the New York Bight, using the IA 15 megawatt turbine and the UMaine semi-submersible open source design. And so that work was presented last year at IOWTC in Boston. They saw a reduction in chain size from 200 millimeters to 165 millimeters by including this C-spring. They're also, just for costing purposes, exploring a taut mooring design that's including a C-spring. And so that design won't be evaluated to the same maturity level as the catenary system was, but it'll provide another interesting data point for the cost assessment that's going to be happening next year. And so the table here just gives a summary of the differences in the mooring systems with and without the C-spring. So in addition to the reduction in chain size, they also saw a reduction in the required line length for the catenary system. So because there was less peak loads, you had less pickup on the line, so you didn't need as long of a mooring radius. So that reduces the amount of chain as well as the diameter. And then Principal Power, we also performed a mooring design using the C-spring. And so the way that this was done is we first designed a baseline mooring system. So following our traditional Principal Power's assumptions around mooring design, we started with a catenary system, and then typically we include a small section of HMPE rope near the platform connection. That's less for the stiffness and more just for reducing pretensions and things like that. Given the site, we ended up looking at a 6-line system, so there's 2 lines per column, or 6 lines total, and then drag embedment anchors. This was designed to ABS standards, and we looked at key design load cases, both ultimate limit state cases, accidental cases, and fatigue cases. What we found is the design was driven a lot by the fatigue performance of the system. So given the smaller 50-year conditions, the chain size was really driven by the fatigue life of the mooring system. And so the plots, what we have here is showing that by adding this load reduction device into the design process, you're introducing more design variables. So it does take more work to iterate through and find, the best system to reduce chain size and to have, the best results for the design. And so what we can see here is looking at different C-spring load ratings, but then also different pretensions. How does the fatigue damage change? But then also how often are we getting to that maximum load of the C-spring where the metalwork is engaging in the ULS cases. And so there's a balancing act there between, trying to find where you get the best fatigue life, but also, making sure that we're not having too many of these lockout cases that, may lead to durability concerns in these ULS cases. And so that design, we ended up settling on a C-spring size and iterating on that. And I'll also note that the inter-array cable was analyzed for both cases here to make sure there were no significant impacts on the array cable by including the C-spring. So here's a comparison of the mooring systems. So we have the baseline system, and then we have our first pass at a design with the C-spring, and then an optimized C-spring. And so what's shown here is in the upper left is the ultimate limit state load utilization. So between 0 and 1, 1 would be the maximum utilization. And then we also have offset, and then we have the fatigue utilization. And so what we end up seeing here is by finding that optimized system, we're able to reduce chain size. So in the baseline catenary system, we had 185 millimeter R3 chain. That's pretty big chain, and it's going to be a challenge on the supply chain if you want to develop a farm for that. But if we include the C-spring, we're able to reduce that chain size from 185 millimeters to 150 millimeters. There's a lot more suppliers capable of making 150 millimeter chain than 185 millimeter chain. It also, we're able to reduce, similar to NREL's results, so we're able to reduce the required chain length as well. So what we end up seeing is a total difference in chain weight in tons from almost 1,700 tons down to 900 tons of required chain for the mooring system. And then, so just a summary of the design for our Principal Power, we saw a large reduction in fatigue damage. We did also see a reduction in ULS case utilization. The fatigue damage was a little bit more spread throughout the line rather than having a hotspot right at the touchdown point. We had a small reduction in the mooring radius, a 45% reduction in the weight of required chain, which translates to almost $1 million savings in chain. But there are a couple of things that we still want to understand as we progress with this project, which is to really understand the ALS conditions with this C-spring and to really understand the fatigue integrity of the C-spring. And then we did see a small increase in cable loads when we moved to the C-spring, as it's a slightly more compliant system. So while it was still within our load envelopes, we did see a small increase in those inter-array cable loads. And then so as we move from kind of a desktop study, the second half of the project is really looking at a large-scale component testing of the C-spring. And so TFI had been manufacturing about 100 of these C-springs. They're doing a large-scale short-term deployment in Europe. And as part of that, one of the springs was sent over to Aker Solutions facility in Mobile, Alabama, to do a large-scale component test of this C-spring. And so this test happened this summer. The objectives of the test were to verify the load displacement response of the C-spring and then perform durability testing at large magnitude load cycles. So as I mentioned before, this polymer component is well understood to have very high fatigue life at those like low load magnitudes and really high cycles. The bigger unknown is the large load cycles that you have like less of during a deployment. So the testing really focused on those high magnitude, low cycle count fatigues. And so that was tested with these 1,000 cycle load level tests where you would run 1,000 cycles at one load level, and then you would increase that load level and run another 1,000 cycles. And we did that at 4 different load levels. And so from those durability testing results, we tested the spring until failure, which was, as TFI said, the design of the test. They really wanted to know at what point it would fail and what the failure mechanism would be. And so the failure mode here was the polymer weld separating. So the way that this is manufactured is each half side is plastic injection molded, and then they have to plastic weld it together. And then so it's at that weld that it just started to separate a little bit. And so what we see here is this is the first 1,000 cycle load limit test. You can't really see the individual cycles when you show all of them, but zoomed in is here. And so what you see is just a very gradual change in load response as the polymer heats up a little bit, and then it reaches a steady state response. The bottom plot here is showing what happened as that weld started to split a little bit. And so what ends up happening is you don't have a catastrophic failure of the device, you just have a little bit of reduction in the load response. So what you see here is these 2 steps is where you see like a little bit of the weld splitting. And so at the end of this 1,000 cycle load test, we stopped the test. And so now we're working with TFI to understand how these findings here map to their previous understanding of the durability testing and see if any required changes are needed to be made either on their design side or how we evaluate the fatigue life when we are doing our mooring design. And so future work in the next 6 months will be, continuing to work with TFI on understanding those durability results. But also we're going to be performing some cost analysis, both with NREL and internally in Principal Power. So we're going to be taking those initial mooring designs and seeing what is the impact on levelized cost of energy for the mooring systems. And then also we're going to be working with ABS on that approval in principle for the mooring system design that includes the polymer spring. And then that is all I have today, and I look forward to your questions at the end of the session.
Hi, everybody. Good morning. Unlike the others, I'm not talking about one specific project. I'm talking a little bit more about the wider NOAA-DC portfolio. So you've already heard today, and if you joined the morning session as well, you would have heard another summary project from the University of Maine. So we've now had 3 of our moorings projects, but NOAA-DC is focused across lots of different activities, and moorings has been one area that we've got a number of different projects on. So I work for an organisation called the Carbon Trust, so not directly NOAA-DC, but we work very closely with NOAA-DC and the team, including working in the R&D committee, which has a number of states involved, developers, various other supply chain companies, and we're involved with sort of the wider portfolio of projects. So the first thing to notice on this is you may be aware, if you've been to some of these sessions in the morning, that we have an R&D roadmap. This is updated fairly regularly, about every 2 years, to pick up on what are the key research projects and the types of activities that we want to do as a bigger group. So that goes into 3 different pillars that are listed here. And the mooring projects that we've been speaking about mostly sit under that pillar 1, so the offshore wind farm technology advancement work. The most recent version was released in April, and you can access that on the website. So that's freely available and easy to find. If you do want it and you can't find it, just let me know. So we have 6 projects so far that sit under the mooring technology category. The 2 at the bottom we went through this morning, so the 2 on Principal Power. If you were around this morning, there was one from the University of Maine, so that was the design and certification of taut synthetic moorings for floating wind turbines. So I'll only give a very brief summary of that one. And then we have 3 other projects, so 1 that's open and 2 that's closed. The other thing that sits on the website, and I'd very much encourage you to look at that, is if you want any further information, we tend to put the final report. So they're often an executive summary, but sometimes they're longer than that as well. So if you want more detail, go there for the first point. And then if you can't find any information or you'd like to speak to the project teams, again, talk to me or talk to any of the NowDC team. There's a couple of people floating around today if you haven't spoken to them already. And they were the various project managers for the projects, and they can also give you more information or put you in contact. So more point of contact than anything else. We have a couple of projects on this in terms of the different aspects of the mooring system. So we have projects that work on the actual technology, so looking at alternative designs for the various different mooring lines. We also have projects around the configuration, so looking at shared mooring designs. There's more to do, and I'm sure we'll pick up on that in the discussion later, but those are sort of the 2 main categories that we've been looking into more recently. And so what I will do here is just give you a very brief overview of these projects, so that we have more information, I said, online for those ones that are closed. And the open ones, I suspect, if we have the NowDC symposium next year, you'll probably hear from the project leads on those then. So this first one, this is the one that was presented by Spencer this morning from the University of Maine. So the idea of this one is looking at 15 megawatt turbine and looking at alternatives to steel. So really looking at the synthetic side, and there was lots of discussion around the nylon use of material there. One of the benefits of this is that it's potential for lower weight, easier handling, different storage, looks at the various different supply chain options as well, so that's another consideration. So there's lots of benefits within that, but we know that we need to test it further. So that project did have an actual test going through on that one. So that was scale model and then the full-scale rope testing. But again, you might have seen the impressive pictures, and potentially you can speak to him later to see the video of that exploding. The second project is one called Intelligent Mooring Systems for Floating Offshore Wind Platforms. So part of this picks up on the presentation that you've just heard, which is around looking at within a floating wind setting, so an offshore setting, the different loads are quite complex, and we need to look at different types of technology to manage that. And on this particular one, it's really understanding whether we can have different systems, and on this case, it acts like a shock absorber that sits within the mooring line technology and tries to reduce those different dynamic loads. So this one was actually a really interesting project and is a good example of a collaboration. So this sits under the UK and US collaboration. That there's a current solicitation open at the moment, but we've done a previous round of that before. And so this was working between UK and US various different research teams on a specific project. And we hope to do more of these in the future. So do have a look at that. And this won't all just be a plug on various different NowDC activities. And the outcome for this one is looking to really advance the system through TRL6 at sea testing. And a big one for that one will be around comparing it to conventional oil and gas systems, and where those can be very capex expensive. You know, like the capex side of it can be very costly. By having new types of technology, once that's tested and qualified, which is something that still needs to be done on this front, means that this could actually reduce the cost quite significantly if you look at it at the whole system. And I should say on that previous one, their website has some good videos as well and footage about how that works. The third project is techno-economic mooring configurations. So on this one, this is one of the closed projects, and that report can be found online if you want to look into that in more detail. So that one has been looking at around what are the cost savings of the technology along the mooring line. So rather than just having a single type of material, so either maybe steel or synthetic, this is a combination. So on this you can see that we've got chain for the anchor and then polyester and then heavy chain at the top. So that's a mixed technology along that, mixed material along that mooring line. The benefits on that could be for a similar thing in terms of there's cost savings there, there's potential for ease of handling, but we need to do lots more testing to really try to certify and qualify this type of technology. So it's not new, but it's also understanding actually what are the different performance windows that these mooring lines can operate in. So the outcome of this was to come up with various different topologies and looking at actually what could that impact look like. And their initial outcomes showed that with synthetic lines, they could actually save 3 times, it could be a 3 times lower cost installation compared to conventional chains and steel mooring lines. So that's obviously a significant saving that we can have if that's used. So that's definitely one to consider along with the other types of technologies and different systems to pick up on the potential supply chain issues as well. Then the final one that I want to pick up on here, I won't go into the Principal Power ones in any more detail, is the one from NREL, so looking at shared mooring systems for deep water floating. So where the other ones have been more on the individual mooring line, this is more about the configurations. So we had a little bit more from the first presentation today around the different types of systems, so how you look at the shared mooring lines, but also on the anchor systems as well. On this one, it was looking at the feasibility of using those. And again, that report is public and on the website, so you can see those different topologies that they've put together. And the benefits there are cost saving, obviously, if we have fewer of them, but it's also looking at those alternatives of what's the impacts on the loads, how will it change within the water, really understanding actually what are the different types of configurations that we can use. So for that particular project, that was looking actually on the west coast, so the north coast of California, and had a simplified water depth of 600 meters. So where some of the other projects have looking maybe more at the shallower water or the mid water depths, this has been looking at deeper water. And this showed that actually using shared mooring lines, as we heard before, could actually provide quite significant cost savings. And this one actually showed that by using the shared anchors as well as the mooring lines, that we could reduce the mooring system installed cost by over 25%. So in a similar sort of vein, that we're really seeing that actually if we can be happy with these systems, and that includes any redundancy, so if a line fails or an anchor fails, that we're still sure that the safety margin still exists, that then this is something that actually as a whole system could be very cost effective. And if we start to have these sort of cost savings, then the whole cost of floating offshore wind will start to see reduced, which is obviously an important part for building out the technology further. And on that, I think I will pass back to you.
Okay. Thanks a lot to all the presenters. I think we have the Q&A part of the session now. So I would like to invite all of you here to the middle to take your seats here. I'll stay here. Okay, first question is related to, I have a few questions which are a bit more general, right? And the first question is about comparing a little bit East and West Coast, right? So we know that East Coast is kind of generally more shallow water, whereas West Coast is generally more deep water. So my question is, if you were to kind of identify top 3 challenges and related to deep water, West Coast, and East Coast and shallow water, what would they be, and would they be any different? You know, so are those top 3 challenges different for East Coast and West Coast? So, anybody, whoever would like to go first, please do.
I mean, I'll open it up for what the West Coast challenges are, and the big one there is, well, 2 big ones right there are the water depth. The high water depth is going to increase your material costs required for the mooring system. Just deeper water, you're going to require more material, and then just the installation logistics, the ports, the availability of everything you need to do the project execution. Are paying out there. So if you can imagine, if you need more material to be able to moor in deeper water, you're talking about more frequent trips to shore, because you can't have as much material for all the platforms on the work vessels as you would. So that would present a major logistical challenge.
Yeah, and then in shallow water, kind of the main driver of the mooring designs is loads. So you see, and this is true in the 40 to 60 meter water depth, but it really applies, you know, as you go to 200 meters of water depth. Your mooring design's load and fatigue driven, and so that drives chain size, which is a manufacturing capacity constraint, but also higher loads means larger vessels to proof load your anchors, and you need to carry that larger chain out to the site and things like that. And so that's why we see, whether us looking at load reduction devices or, you know, in the previous presentation, trying to use nylon. I mean, you can think of nylon as essentially another load reduction device, a way to try and to reduce those peak loads and capture that fatigue life, to reduce, you know, the required load capacity of your system. And so that load capacity, it does relate into what Bruce talks about, this, you know, the same logistical concerns. It's different reasons that those logistical concerns are driven, but it's still going to be a challenge on either coast.
Yeah, and I think as well, in terms of the logistical side, it also picks up on the O&M perspective. So if you're looking at deeper water sites, it might be further, but not necessarily, depending on where the shelf is on the west coast. But actually looking at the O&M aspects, that's going to be similar in terms of that's a big driver on how we're going to access multiple different turbines. But we've also got knowledge, at least from the oil and gas side, in terms of how do we get out to these systems, what do we need to look at. It's just that we've got a lot more of them.
Okay, well, thank you. And I have a follow-up question to this. So if we, hypothetically, if we had a lease in the West Coast and in the East Coast, right, and we needed mooring system solution like tomorrow, would we be ready to, do we have those technologies already ready for, and is there a difference for both coasts? Or if not, you know, is there a significant difference in terms of when will they become mature for each coast?
Yeah, I can start with that as a starting point. So I think, I mean, from looking at the work that we're doing through NowDC, there are technologies that exist. I think maybe we're aware that more work needs to be done on some of them, but I probably see more of the challenges sitting on the qualification and certification and making sure that that's up to speed and that you know, we know that they can operate. So there's a certain level of research and development that needs to happen, but it's also actually on the certification side. But I don't know, do you agree?
I'd say the other just really big one is just the case of volume in the supply chain. It's you're talking about miles and miles of rope, miles and miles of very large chains. And if you look up, talk about leveraging lessons from the oil and gas industry, where you've seen significant amounts of chain failures over the years, and the quality requirements are now being required to produce that amount of chain in the sizes we're talking about here at scale. I think it's more of a logistical and supply chain issue than a technical one. At least on the deep water side, that's all going to be commercial off the shelf.
Yeah, and I guess what I would add to that is, you know, PPI has a track record of mooring systems and pre-commercial projects that have been designed in these intermediate water depths. In addition to the supply chain concerns, it's also a cost concern. So a lot of these technologies we're looking at are attempts to find solutions that reduce the cost. So there are solutions out there, particularly in intermediate water depth, that have been shown to work, at least for not a full 30-year deployment yet, but we have a couple years of experience now. So now it is a supply chain and a cost constraint more than it is something that can work.
And maybe just another point on that in terms of the comparison with the oil and gas side, and that in terms of we've got a long history of using lots of these technologies, that some of them need to be adapted maybe, but we do have quite a history of using it. But again, it's maybe more that there's a level of cost reduction that we need to do within floating offshore wind, purely by the number of different turbines that we have out there. So with oil and gas, that if you only have a limited number in the sea, you can have more at a higher cost because it's not making such a big impact on the overall project. But within floating offshore wind, because we've got a high number of them, that we need to reduce those costs because that will have a big impact on the overall project cost.
Just a note on that. I mean, we talk a lot about reducing costs, but it's also reducing costs without reintroducing unnecessary levels of risk, because your failures create downtime. It's a huge economic hit just off the bat, before you even talk about potential for long repair times, because you get back into the whole issue of long lead times for critical components. So it needs to be an economic issue, but it also needs to be done from a risk and reliability standpoint as well.
Okay. Thank you. Another question is, how do we advance floating offshore wind and I guess mooring solutions more quickly? What are the ways we could achieve that? How can we accelerate?
Well, the reason why we're sitting here is through NowADC. So at a simple level, maybe more on the collaboration side. I mentioned one of the projects that we're doing between the UK and the US. I think there's more opportunities for that in terms of the international side. There's lots of expertise from Europe, but that doesn't mean it only sits there. And particularly on the deep water side, that's relatively new. We haven't had the same rollout, at least on those sort of early stage projects yet. So there's lots to be done around actually shared expertise. But also the sites, I think. So whether we need more tests and demonstrations, that's something that is something that I think we need to collectively agree on, but also is something that we can work on between different countries and states that we probably don't have enough time or capacity to do it within a specific area.
Well, there's that, but then also to be more direct about it, I mean, one of the quickest ways to accelerate this is the existence of actual projects to put steel in the water. I mean, we can talk about the development and everything else, but most of these developments, a lot of the lessons learned that are going to be required to deploy this are going to come from the actual project constraints.
Yeah, and if I can add to the using an actual project, generally speaking, a lot of live projects can be a bit more risk adverse, so it's a little bit more challenging to get a novel technology in there. So if a developer, say, looking at, a gigawatt scale farm and is willing to do, 1 or 2 turbines and try a different mooring technology, even if it's not planned to be 30 years, but maybe you're going to put a load reduction device or try nylon or something else for 2 years and have a planned intervention after that. Because I think one of the big gaps is going from these bench tests where you can understand the short-term performance, but the real gap is understanding how that novel technology is going to age and perform at the end of a 25 or 30-year farm life.
I think maybe we definitely need projects in the water. I think that's clear. But maybe something around the standards and the guidance side of things as well. So once we've got these things in the water, actually trying to accelerate through best practice and having guidance and clear guidance that works across multiple farms, that we're not necessarily just designing for a single project, but that's something that could be rolled out across multiple projects, multiple countries. Do you agree with that?
Definitely.
Okay, thank you. Next question is about the technology innovation gaps. If there are any specific innovation gaps, and kind of to inform, future roadmaps for research and development in terms of, mooring lines, what would that be? Just some examples. I
can start with what I know is in the roadmap. So I think more needs to be done actually on the shared mooring side. We've talked a little bit about that already in terms of the different configurations and what those mooring systems look like. But I don't think we're at a point, and you may disagree with that, but I don't think we're at a point that we know exactly what needs to be used for each project and what is the actual optimized system. So I think in terms of what needs to be done is probably more actually doing fundamental research, but then actually looking out at sea as well. So it's starting to build it up to the next stage and not just a theoretical desk-based study, but the next step up.
Big one would be ways of just getting cost and time down. Things that can be rapidly installed with minimal intervention, with smaller vessels that are more easily available, so you aren't as beholden to the very limited supply of specialist vessels out there.
Okay, thank you. So I'm going to move on to the questions from the audience, and we have already a few questions here on the list, so I'm going to start with those questions. So if you have any questions, please submit them to use the QR code and submit them through the Slido app. First question is for Bruce. What percentage of wind plant capex did you assume the anchors and mooring comprise?
I'd have to double check the exact numbers, but I believe it was somewhere between 3 and 5%, depending on the water depth in the site and the number of turbines we're considering in the farm.
Okay, thank you. Next question. I think this question was already asked this morning, but the question is, why would somebody use floating wind technology at the range of 40 to 60 meter water depth?
Yeah, there may be geotechnical concerns with, different pile concerns and things like that. But the other thing with the shallow float project is we really hypothesized that to stress test these load reduction devices, like pushing to a shallower water depth would really provide a good stress test and understanding of that. And you kind of want to push at the limits of your design space to understand everything further.
Okay. Next question. Looking at the O&M, are we then ready for these large-scale floating wind developments? Question mark.
Is that the chicken and egg problem there? That if we try to fix everything first, we'll probably never deploy at scale. We already have some demonstration sites out there, and we have some bigger sites that are planned. So I think O&M is something that we can definitely plan for, and is probably one of the big drivers of how do we actually get out, how do we look at surveying the different mooring lines. I think working with the insurance side, developer side of actually how many do we need to survey? Do we need to survey every single line? At what time? These are things we can think about, but I think, from my opinion, is probably we need to get something in the water and start actually working it out. And we've seen that from fixed offshore wind as well, that over time the O&M aspect has been optimized much further from the beginning.
All right. Thank you. Next question, I think, is for Bradley. How big is a sea spring for offshore wind? Does it ship in a standard container?
The one that we tested, which is about suitable in size for, say, a 5 megawatt turbine, did ship in a standard container. When you start looking at 15 megawatt scale, it'll depend on the site. Again, as I showed, the load rating is a design variable that you choose as a designer. It will be, about in that size of maybe it'll ship in a shipping container, maybe not, depending on your load rating. But the other thing that TFI is advertising is, since they're using standard injection molding facilities, that you may be able to manufacture that close to the port that you're using to reduce some of that required transit.
Okay, thank you. Next question. In the last session, we heard about nylon pros and cons. For deep water applications, are there any other considerations for nylon application?
Deep water for the most part, polyester has been seen to do a pretty good job, and it has a much longer track record, and we don't tend to see the need for the increased compliance that you would need to see in shallow water. So I think the use of the demand for nylon in deeper water is a lot less.
Okay, so we actually have no more questions from the audience, but I have one final question about costs. And I know it's a tricky question, so we can have a bit more general discussion, but, I think one thing is, we as developers, we need to make cost assumptions when we are preparing our models, so we need to have cost assumptions today, right? So how robust cost assumptions can we have today? I'm not sure how difficult or easy it's to answer that question, but let's see. And then the second part of the question is what is the biggest element of cost? Is it procurement or the components, or is it the installation cost? And is there a difference for shallow or deep water?
I can start with one point to consider, which is around the AEP calculations, so actually looking at the energy that's coming out of a wind farm. That one, I think, and I'm not a developer here, so please speak up for others, but I think that's something that actually that's already quite complex, that if you look at the yield side of things, if you look at the wake effects, that's not an easy environment to model effectively. If you then start looking at floating offshore wind, you've then got the subsea aspects as well, and what that impact is. And at the moment, I don't believe the mooring technology and the impact of mooring lines is actually considered within that calculation. And so in the future, that's quite interesting, because that means that moorings could then start to become part of, or mooring technology, mooring configurations start to become part of that calculation. And that's something that doesn't give you a clear answer there, Roger. But I think in terms of how complex that is, I think as we get more information on how these will run, and that comes from actual testing and demonstration and from the commercial projects, then we'll probably have a better idea on that specific cost. And it's probably quite a broad envelope at the moment.
Yeah, I think if we focus specifically on mooring component and deployment costs, it's kind of challenging right now. Costs are shifting a lot with inflation and things like that. But generally speaking, if we can move more towards standardized material that's used in other industries, namely oil and gas, you'll have more cost certainty than if you're using larger diameter chain that's not as frequently manufactured. On the deployment side, there is a pretty big variability in day rate of vessels, because it's driven by how much vessel demand there is on that day. So that's something we've seen in our European projects is it's hard to know the exact day rate that you're going to pay, because it depends on what else is happening that year and what the demand is of those vessels.
And maybe just on the vessel point, is that something that at the pipeline of projects, how does that impact? Because from the mooring perspective, if you're looking at mooring and anchors, if you're looking at the handling of that, how do they fit on conventional vessels? If we're getting bigger, we may need more specific vessel types. And then do we have that ready? That pipeline of projects, is it something we need to invest in now? And I suspect that answer is yes. So probably more in terms of the domestic side of things and how to build out the capacity for the actual vessels.
Yeah, so I'm not super familiar with the capabilities in the U.S. Generally speaking, the higher your loads are, the larger vessel you're going to need. If you're using drag and bendment anchors, you're going to have to pull on that anchor up to the maximum expected load. So the harder you have to pull, the larger vessel you need. The larger your chain size, the larger vessel you need to hold the chain. So all of that kind of plays into your vessel size. That's one of the reasons there's so much interest in driving down what the required chain size is, because that flows down into your anchor size, it flows down to your vessel size, and all of that. It's not just the material cost of the chain.
And then the other part of it too is just going to come from once we've got all that figured out, it's the supply chain maturity. So as the expectation is that as we're using more and more of this, the economies of scale are going to work in our favor. But the project pipeline has to be established for, we heard yesterday, for these investments to be made in order to achieve these cost reductions. So it is a little bit of this chicken and egg problem.
Yeah, and I guess what I would add to that too is back to my earlier comment about vessel day rates. You know, a lot of our prior experiences, pre-commercial projects where we're looking at 3 turbines or 5 turbines, a project can't afford to, you know, commission a new vessel for that. But if we looked at fixed bottom offshore wind, you know, if you start looking at very large projects, it may make sense to, you know, plan in advance what kind of vessel you're going to need and either procure that or, you know, work with someone, you know, maybe it's more of a developer question than on our side, but that might lead to more cost certainty looking at larger deployments.
And to the point about where the costs sit, I think the CapEx part is still in that. If you're looking at the big equipment parts, that's where cost sits. So you're looking at the mooring lines, you're looking at the platform like that. That's where it comes from. But we've already picked up a little bit on the vessels, whether that's O&M or the construction side, and also in terms of the actual O&M, the personnel, all that side of it. There are a lot of costs there, and I think there's a lot of potential for that to come down, whether that's through more of these sort of collaborative projects or whether it's more on the deployment side. But I think both of those costs need to come down, and that's probably driven by domestic infrastructure, government support. We've got the wind shot challenge that I think we've heard about several times on that from the US side, but also what's happening in other countries as well.
Okay, great. Thank you very much. We ran out of questions, so I would like to thank the public for submitting your questions. I'd like to thank the panelists for their presentations and answering questions. Thank you so much.